All right. Good morning, ladies and gentlemen. Welcome to this series of online lessons. Today, we're going to look at mathematical induction, and basically, this is one of the methods that we use to show whether a statement is true or not, or rather, to prove whether a statement is true or not. And for mathematical induction, we only follow three steps, of which the most important steps are step 1 and step 3. So in step 1 and step 3, this is where we show that the statement is true for n equals to 1 for step 1. And basically, it's not just for n equals to 1, we follow the domain that we've been given for the question. Okay, so if the domain is starting at n equals to 1, then step 1 will n equals to 1. If the domain is given that n is starting at 2, then we are going to follow that n should start at 2. So step 1 and step 3 all have to be verified, or all have to be true for the statement to be true. So meaning that if we are on step 1 and the statement fails to satisfy step 1, we can conclude that the statement is not true if it fails to verify step 1. So step 2 is the assumption step. This is where we assume that the statement is true, because we are just replacing the same value of n with k. So we are not changing anything. So step 2, we just replace the value of n with k. So this is where we confirm, or let me say we assume that the statement is true, because we are not changing the question. All right, so let's look at some examples here. So we're going to have these two examples that we're going to look at. So determine if the following statements are true. So we have the first statement, which is the sum from n equals to 1 to n equal to n open brackets n plus 1 over 2 for n greater than 1. So here we see that we've been given a domain, and that domain is that n is greater than or equal to 1. So for this one, we can start at 1. If the domain was given as greater than or equal to 2, it means that we should start from 2. Okay, so that is that. So the other way of writing this is just this: when n is 1, you replace here. You're just replacing this into that. So when n is 1, we're going to have 1. When n is 2, we're going to have plus 2. So sigma indicates summing, plus 3, and so on and so forth to plus n, as we put n there. And this should be equal to n open brackets n plus 1 all over. Okay, so that should be equal to that. Okay, so now we'll start with this, the first one, the a. So I have written a few here. So a, we have 1 plus 2 plus 3 all the way to n and equal to that. So when you have a series like the way you were given like that, make sure you expand it. It will be easier to work out things. Okay, so we have 1 plus 2 plus 3 plus all the way to n is equals to this. So now for n equals to, for n greater than 1. So now if we are proving by mathematical induction, we need to state by mathematical induction. So step 1, we need to show that the statement is true for n equals to 1. So we replace. When n is 1, we're just talking about the first term. Remember, when n is 1 in the sequence, it is when we replace 1 into sigma of n from 1 to n. So when n1, we're just talking about n equals to 1, and we're going to have 1 on the left-hand side. So this is the left-hand side. When n is 1, we're just going to have the first term here, which is 1. That is on the left-hand side. And on the right-hand side, when n is 1, for n equals to 1, on the right-hand side, we just get the right-hand side as it is. Where there is n, we'll replace with 1. So this would be 1. 1 plus 1. When you simplify that, 1 plus 1, you're going to get 2. 2 times 1 is just 2. Then when you divide, we see that we're going to have 1. And therefore, the left-hand side is equal to the right-hand side, because the left-hand side gave us 1 and the right-hand side has given us 1. So we conclude to say the statement is true for n equals to 1. Then now we'll go to step 2, okay, which I'll write here. So step 2. Step 2 is the assumption stage. So we just assume true for n equals to k. So this is the assumption stage. So remember we have 1 plus 2 plus 3 plus all the way to plus n equals to n open brackets n plus 1 all over 2. Then for n equals to k, we're replacing wherever there is n with k. So we're going to have 1 plus 2 plus 3 plus all the way to plus. Here there is n, so we replace with k. So this would be k, then equal to, so here there is n, so that will be k. So that is k. Then here there is n, so that will also be k. Then we're going to have like that plus 1 all over 2. So wherever there is n, we've replaced with k. And we're done with step 2. We're just assuming that the statement is true for n equals to k. And why we're assuming is because we've just replaced n with k. We've not changed the statement, so we can just leave it there. And now step 3, this is where we have to show that the statement is true for n equals to k plus 1. Step 3, show true for n equals to k plus 1. And always step 3 works hand in hand with step 2. So step 3 will make use of step 2 at some point. So you have to be very, very cautious of that, and you have to remember that always. Okay, so first of all, we write what we have. So we have 1 plus 2 plus 3 plus all the way to plus n equal to n open bracket n plus 1 all over 2. Then for n equals to k plus 1, okay, first of all, when n is k, you're going to have this part, okay? That is when n is k. Now, let me write this. For when n is k, you have to remember this. When n is k, you're going to have 1 plus 2 plus 3 plus all the way to plus k. So this is when n is k. Okay? Then when n is k plus 1 will be this k plus 1. So it will be k plus 1 like that. So there will be another term there. Okay? So that is how it will be. When n is k, you're going to, it's more like when you have 1 plus 2, 3. Okay? What is 3 plus 1? 3 plus 1 is just 4. Okay, so that is what this statement is. So even in all sequences, so when you reach this stage, you're going to write from 1 to k. Then the k plus 1, you just replace in n here, you say plus, you replace in n k plus 1. So that is what you'll be doing. Okay, so now having that said, we've replaced k there will be this. Then k plus 1 will be the number after k. Okay, so that is what you should do always. And on this side, we can replace n k plus 1 will be k plus 1. Then we're going to have k plus 1 all over 2. So this simplifies to k plus 1 times k plus 2 all over 2. Okay. Now, we have 1 plus 2 plus 3 plus all the way to plus k, then plus k plus 1. Okay, so we have that. Now we need to pick a side that will produce the other side. So we can choose this side to produce this side. So this side is the left-hand side. So we say left-hand side is equal to 1 plus 2 plus 3 plus all the way to plus k, then plus k plus 1. Okay, then you see that this up to here from step, we see that it has some variable. So from step 2, 1 plus 2 plus 3 plus all the way to plus k is equals to n open brackets n plus 1 over 2. So we see that from step 2 here. This is why I said step 2 makes use, or step 3 makes use of step 2. So now, meaning that we're going to replace this part with this. So meaning that now the left-hand side will be equal to, so this part will be replaced with this. So we're going to have n open brackets n plus 1 all over 2. Then there is this term here plus this term here, k plus 1. Sorry, it's k here. So k, k. Okay, even here, k. So from step 2, remember we replace with k. So everything should have k from step 2 here. From step 2, we have this part that has k equal to this part that has k. So we replace this part on the left-hand side in step 3 with this part here. So it will give us that. Then here we just have to simplify. So simplifying this, we're going to have, so here common denominator will be 2. 2 into 2 is just 1. 1 times everything on top. We can distribute this in advance, or we can just say k, just say k open brackets k plus 2, I mean k plus 1, then plus 1 into 2, that is 2. 2 times k plus 1, it will be 2k, 2 open brackets k plus 1. Okay, we can do it like that. Then we see that we can factor out the k plus 1. So we factor out k plus 1 on top here. See that we factor out k plus 1, k plus 1. We're going to remain with k plus 2 all over 2. And this is actually equal to the right hand side. So this is the right hand side. We see that, eh? So this is equal to the right hand side. So we just say equal to right hand side. Okay, so meaning that we've showed that left hand side is equals to right hand side. Then we make a conclusion to say true for n equals to k plus 1, since the left hand side is equals to the right hand side. Then you make a conclusion. Always make a conclusion. Conclusion. Since true for n equals to 1, n equals to k, and n equals to k plus 1, the statement is true for n. For all all values of n for all n. Then that's it, you're done. Okay, now let's attempt the other question as well. Let's attempt the other question as well. So we have, we are going to show that 2 a to the power 2n minus b to the power 2n is divisible by a minus b. Okay, so that is what we're going to show. So showing for divisibility, we let a to the power 2n minus b to the power 2n be equal to some constant. We can even say m times whatever we are asked to be divisible by a minus b. Okay, and in all cases we are going to be dividing that term by that to show if m will remain as a single value. Okay, so if this number is divisible by this number, m will remain as a single value, and on this side we're not going to have any remainder. That's the idea. So we'll divide by a minus b on both sides, a minus b, and on this side we're going to have no remainder. There won't be any remainder. Okay, in other words, it will be a linear function. It won't have a quotient. There won't be any quotients when we divide. Okay, so that's the idea here. So again, 3 steps. Step 1, show true for n equals to 1. So true for n equals to 1. We have the statement a to the power 2n minus b to the power 2n equals to m a minus b. Okay, so remember, we let m be some number such that when we divide this number and this number, that number is not a quotient. Okay, it's just a real number. It's not a quotient. It's an integer. Okay, we can even put here to say m is an integer. Let me write here. M is an integer, meaning that when we divide this and this, m will not be a fraction. Okay, so for n equals to 1, we replace wherever there is n with 1. So we're going to have 2a to the power 2 times 1 minus b to the power 2 times 1 equals to m a minus b. Now we see that on the left hand side, this is the same thing as a to the power 2 minus b to the power 2 equals to m a minus b. Okay, now this here, you know it from somewhere. This is the difference of 2 squares. So this is the difference of 2 squares, which can be written as a minus b times a plus b. So this will be equals to m a minus b. And when we divide both sides by a minus b by a minus b, we see that this and this will cancel, this and this will cancel, and m will be equals to a plus b, which is a linear function. So true for n equals to 1. So true 1. Okay, so we've done the first step. True for n equals to 1. All right, so now we go to step 2, the assumption step. So assume true for n equals to k. So remember, we have a to the power n 2n minus b to the power 2n is equals to some m value that is a factor of that. Okay, so now for n equals to k, we're going to have 2 to the power 2k minus b to the power 2k is equals to some integer a minus b. So we have not changed anything here. So now we go to step 3, the showing. Step 3, show true for n equals to k plus 1. Okay, so we're showing true for n equals to k plus 1, and we have to remember what we have, which is 2 to the power 2k minus b to the power 2k is equals to some, let me start from, we have a to the power n minus b to the power n, 2n, is equal to m a minus b. So this is what we have. A to the power 2n minus b to the power 2n is equals to m a minus b. Then we say for n equals to k plus 1. So we replace with k plus 1, we're going to have 2 to the power, a. This should be a, sorry. Is it the same mistake that I was making here? So this is a. Apologies for that. So that is a to the power 2k. Okay, here we were okay. Okay, so a to the power 2k, b to the power 2k. So same applies here, a to the power n, b to the power n. Okay, we are okay on top here. Okay, so it's supposed to be a. Where there is n, we replace with n plus 1. So this would be 2n plus 1 minus b to the power 2n plus 1 should be equal to some m a minus b. Okay, so some m. This is, since we've increased the number, this will be a different value here. So we say some r. We'll say some r such that when you multiply that r with a minus b, it will give you this side. Okay, so that is the idea here. Again, r is an integer. Okay, having that said, we can start simplifying. So we need to show that this is also still divisible by a minus b. So for divisibility, we need to show. So on top there, we have a raised to the power 2. We expand that. That was 2n plus 2. And that side will be b raised to the power 2n plus 2. And this will be equal to r of a minus b. Okay, now you can use indices here, and note that this is the same thing as a raised to the power 2n, open brackets, a raised to the power 2 minus b raised to the power 2n times b raised to the power 2. So using indices, we can tell that that is the case. A minus b, like that, of which this can also be written as a raised to the power n, okay, times a, then everything squared, minus b raised to the power n times b, then everything squared. And this is equals to r a minus b. Okay, then we see that this is also a difference of two squares. So we have a raised to the power n, a, minus b raised to the power n, b, times a raised to the power n, a, plus b raised to the power n, b, and this is equal to r a minus b. So we're at this stage.